just like a first quick review, last time we saw three different flavors of singularities. First, we discussed the pure, which I'm not going to rewrite the definition, but this should be good enough to remember what it is. Is, you know, the tensor product with the inclusion is always injective. Second, we define a split. Then we have a retraction for this inclusion. We discussed that these two are the same in the affine case, which is the case that we're focusing on. And we discussed F injective. This means that the Frobenius action induced by Frobenius, the Frobenius map on the local homology, is injective, and here we're assuming that the ring is local. So yesterday, in some of the problems, was to show that both purity or splitness are a local property. So, and then here we're with completion. You can see that you want to define F injective for any ring. You can do it like a ring is F injective if and only if all its localization and the maximum ideal is F injective. And this definition is good. It works. I mean by that you take a local F injective ring and you localize, then its localization is also F injective. I'll go through. Good exercises? You may, no. Okay? So today we're going to see a bunch of properties of this and then try to justify why we care about the singularities. Okay. The first one that I want to mention is the Hofstad-Roberts theorem. So let R be an F injective ring, and the right thing, sorry, standard graded K algebra. Remember, this is just a fancy way to say that R is the polynomial ring with the standard grading, modulo and homogeneous ideal. Then our friends from last time, the invariants are always smaller or equal than 0 for every I, and as a consequence, the regularity, as we define it, is because no room for regularity is smaller or equal than the dimension. Okay? So, before I give the proof, I should mention some things. I'm going to give like a very easy proof because we already proved that F pure and F split are the same in the F finite case. The theorem that they did is actually, they proved that if you look at the paper, it says that for F pure, this is true. And they proved that F pure without the F finite assumption implies F injective. So you will see a very easy proof and say, well, yeah, it's very easy to be a theorem, but it's because there is so much work that we're implementing in what we did this equivalence. And if you try to do the lemma from, that we used yesterday to prove the equivalence, that lemma it's not easy, no? It's a fun problem to do. Okay. Okay, so let's do the proof of this specific version. So we're going to proceed by contradiction. Okay, so suppose that there exists an I such that the I invariant is equal to, let me call it T, and is positive. Okay. So if we fix an element B inside the I local homology of degree T, this is possible by how we define F invariant. There'll be a non-zero element Okay? So then, because this ring is F-injective, we have that f of b has to be different than 0, no? And because Frobenius is a graded map, because it sends homogeneous things to homogeneous things, it's not of degree 0, no? It raises, but sends homogeneous things to homogeneous things. And it multiplies the degree by p, no? So this is going to be preserved also in the local cohomology. So the degree of f of b is going to be p times the degree of b, which is p times t. But because this is positive, this has to be bigger than t. Contradiction, no? Because t is the top degree, because that's the invariant. Yeah, contradiction. So the invariant has to be negative, and then we have that the regularity, as we define it, is equal to the maximum of AIR plus I, and then I moves from 0 to D, where this is the dimension of the ring. So if this is non-positive, the biggest of these entries will be I, and the biggest of the I is D. No? Okay. So a fair question that you may have. Okay. Last time we saw different definitions for just no move regularity. I introduced the one with local cohomology, but then I also want to mention something with graded free resolutions, with graded Latin numbers. And if you have experience with Macaulay 2, which I guess now everybody has at least one day, computing local cohomology is a lot harder than computing free resolutions, because in some cases we have algorithms like using theory of D models, rings of differential operators, but then in broader bases are kind of slow. In general, you do that in the Weyl algorithm, in the ring of differential operators, it's even slower, because you have to multiply the number of variables by 2 in a way. So local cohomology is very difficult to compute, because I haven't told you that local cohomology is usually not finally generated, but I just haven't told you that it's finally generated. That rarely happens. So local cohomology is hard to deal with. And the first complaint is, well, when you define has no move for regularity with local cohomology, if it's so much more difficult to compute it, we have algorithms to compute free resolutions, and then they work reasonably well. And then, well, this is one of my excuses. Because if we do it with local cohomology, I can tell you that regularity is always bounded. So the jumps in the free resolution are bounded by the dimension. So the free resolution may be complex, but the degrees, how things change, is not that bad. And the way we can do this is by the definition with local cohomology. So we're not able to get explicit computations, but we're able to get explicit properties. And that, well, it's good that we have two definitions, also we get the best of two worlds. Okay. We're gonna give a stronger version of this theorem later, but for that we will have to make a detour and talk about the field dresser, which we're gonna do today at the end of the lecture. Okay, but before, I want to mention another theorem that I really like. This is by Untitled Chapter. It says the following: let S be a power series ring, with K is prime characteristic, and I contained in S be an ideal, and R equal as S over I. So if R is F injective, then the projective dimension, which we defined last time, of R over S, is bounded above by the number of generators of the ideal. Okay? Bounded number of generators of the ideal. If you have played with free resolutions, there are some cases where this always happens. No? You have a square-free monomial ideal, or actually a monomial ideal, but let's think in a square-free monomial ideal, and you take the Taylor resolution. The length of the Taylor resolution is going to be exactly the number of generators. So this follows immediately for the square-free monomial ideals for the Taylor resolution. But you have a polynomial, sorry, an ideal that is not square-free. This is easy to create counter examples where this does not hold. That's a good exercise to test your Macaulay abilities. So this is in the line that I was mentioning before, no? F pure implies F injective. So I can put here F pure if I wanted. And F pure rings, its projective dimension is behaving as a square-free monomial ideals. But here, the way one may prove this is not using free resolutions. You don't build a free resolution, stuff like that. What one does is compute the top vanishing local cohomology and associate that with certain X modules, and then play a game. You have something with that, Auslandet-Boltzmann formula, and something I'm not gonna do because it's gonna be very involved, and I want to do something else. But anyway, so this is one of those results in which F purity is very similar to standardized rings. Okay, but I wanted to relate this to other theorem. Let me just mention. This gives an easy solution for F injective rings to what was known as the Stillman conjecture, and today is known as the Anand-Hochster theorem. That there was an important conjecture for a long time. So given L, D1, dl with positive integers, then there exists A and B inside natural numbers, such that for any, and this is important, n natural number, or positive, I guess, positive integer, and any polynomials, and any polynomials, f1 integer in k, and then I'm going to do something that Mel likes to do, and I think makes a lot of sense. So we should think that this n is a very big number. Okay? Of degrees d1 until dn. We have that the regularity of R modulo this ideal, I should have said is homogeneous. This ideal is bounded by A, and the projective dimension of R, this is R, sorry, modulo F1 to Fl, is bounded by B. So I'm saying, like, for any ideal that you give me that has this number of generators on these degrees, it doesn't matter where they live. The regularity and the projective dimension is going to be bounded.
Is the n that you want big, very big, or?
Yeah.
The n?
No, L.
N is the number of variables of the ring?
Yes. So, like, for instance, you give me two quadratic forms. It doesn't matter how many variables they are with. As long as I know that there are two polynomials of degree 2, I can tell you this is bounded by this number. You give me 5, And this could be really big. Now, this bound can be like I don't remember, but it could be really big. No, it's not like a polynomial ring or like a polynomial function in the D's. So what we're saying is that from the Vesnick theorem, the result, which he phrased in a different way, but this as a consequence of what he has done in vanishing and local cohomology and other stuff. Then this is just L. If you have an injected, so even this data, the degrees does not matter. What matters is just the number of generators for this very specific case. Okay. But again, it's again when having Frobenius, it helps us to manage things. Okay. Now that we start like playing with the relation between Frobenius of standardized rings, let me do another application to symbolic powers. Okay, and for that I need to make a definition that I be now. Oops. The radical ideal with minimal primes Q1 into QL, then the big height I is thus BH. I is the maximum of the height of the minimal primes. We know that the height of the ideal is the minimum, so we're going to the other direction. So last time we saw, last time, no, on Monday, we discussed harmonic projection. So let me just write it using the big height. So in this setting, so that I contain it in S. Let me write polynomial, what I mean, regular block. This regular blocker, be an ideal, a radical ideal, of big height H. Then I, symbolic I, n minus 1 plus 1 is contained in pi to the. Remember, we know that this is true if we just put this one, no? H times n. Well, we prove it only for primes, but I think this was one of the exercises, like do it in general. If not, you know, it's a good exercise to do. But here is slightly less. Okay, and we know that if we're in prime characteristic, and here we put p to the e, and we here put p to the e, that's true, no? Everyone remembers this from Monday? Okay. Or from the video from Monday? Okay, so, as I mentioned, the conjecture is false. And the first example, was given by Dominik Selsberg, Tytax Jasinska in 2013. And I'm not going to give it here, it's a little bit more involved, but I would like to direct you to go to Eloisa Grifo website, where she has a wonderful notes on a book pretty much of symbolic powers. So where she talks more about this conjecture and these examples. But what I want to do is to prove cases where this conjecture is true. So let me do that first example. Okay, this is a proposition by Bauer. Rocco, Carbon, Kulska, Nielsen, and Sisdek. Okay, and this is the following. Let I be continuing here. L. Here, I'm using polynomial B and square free monomial ideal with its primary decomposition. So I'm writing this as an intersection of minimal primes, which we know every minimal prime is generated by variables. Okay. Probably we need any anyway. Yeah, I think we don't need any. Okay, so then the conjecture holds. So if H is the big height of I, then the conjecture holds. For all, this happens for all. Positive. Okay, so let's do the proof. The proof that I told you that every ring here is prime characteristic, but this proof is going to be characteristic free. What's going to use Frobenius? You will see. Well, Frobenius like morphisms. So if you give me any n, we're going to fix a positive integer and set this map phi sub n that goes from S to S. This is S. That sends every variable xi to xi to n. The constants stay constant, no? Like sends 1 to 1 and c to c, not a map of k algebras. Okay. And this is like a Frobenius-like morphism. No, Frobenius will be raising everything to the p. Here we're just raising the variables to the n. So exercise within the proof. S is a free model over the image of this map. What is this map? This is just k, h1 to the n, xt to xl to the n. Oh, this should be t, because we have to write stuff. And it makes sense. No, what you did with to verify Kuhn's theorem for least power set rings or rings of polynomials in the problem set is pretty much the same idea. So this is free. Okay. Now we're gonna set I bracket n is gonna be equal to phi of n of I s, okay, which is gonna be the ideal generated, but now here I'm gonna look at all the monomials in I. And I want to write it this way because this way is clear that this is contained in I to the n, which we know is contained in I. So this map of K algebras, for this map of K algebras, every monomial ideal is stable. Here is a bit problematic if you want to go outside monomial ideals. No? You take hypersurface, like a principal ideal, that is not monomial, this is going to be false in general. But for monomial, it stays stable. And this is why, if it was the Frobenius P to the E, in one characteristic P, we have the same thing for any ideal. Okay, we're simplifying, we're forgetting about characteristic P, but then things are still true for monomial. Okay. So let's prove the theorem, which we pretty much already did in Frobenius because it's the same ideas. So by work done before, we have that this one, hn minus 1 plus 1, is contained in I bracket P. And by work, I mean the work that you did in the problem sessions. So you did it for P to the E, no? And prime characteristic. The proof is the same using this Frobenius-like morphemes. And this is contained in I to the N. Very easy, no? And this is just one of those examples where you can get results characteristic free, probably stronger, with Frobenius-like morphemes. And there's a bunch of them. And again, if you want to see more examples like this, we have a survey, Alessandro De Stefani, Jonathan Montagno, and myself on the archive that shows more of this interaction of Frobenius in combinatorics. Okay. So if you, you cannot really guess what's going to happen, no? The result is for square free monomial ideas. We should be able to get it for a few rings, no? If this meta theorem that I'm trying to sell is meta theory. Okay, so I'm going to give a lemma that, again, this is not going to prove, but it's fun to do it. By way of unity, says following: let R be a regular ring, and I contained in R be a radical ideal of B height H, and a positive integer, then I bracket P to the E dot I is contained in I symbolic N, I N plus H with P to the E for every E big enough. Okay? So it may fail for 1, 2, 3, but then at some point it's gonna hold. So I'm not gonna leave this as an exercise as it is, but it will be fun if you do it at least for the maximal area to see what you. This is well, no? So show the lemma for the maximal area. If you want to do it for every ideal and then solve the problem by assuming that it's maximal, that's cool too. What do you mean? No, I'm not assuming local, it's just regular. But this can reduce to the local case.
In the exercise, you say show the limit.
Oh, yeah, of course, okay. For regular local, thank you. Yeah, you're right, thank you. Okay. So what's the theorem is this one, but for a pure. Okay. So let S be a regular ring, and I containing S be an ideal behind H such that R is S over I is F pure. So Harman's conjecture holds. Where are we going? Okay. Okay. Proof. And here, without loss of generality, we can assume that S is regular. We want regular because we're working with the pure rings. We want to use Feder's criterion, which applies to a pure. Sorry, to local rings, no?
You mean local?
Oh, thank you. Okay, yes. I know what that means. Okay. Okay. So first we note, and this is a pretty deep observation. Okay. So I NH plus H is contained in I to the n. And let me see what this. We're going to prove this in a moment. But what this is the strategy. So what this is telling us is that to lower the H here, you can lower the H in the symbolic if you pay by putting an I outside. So when we're having over here, we can keep dropping the H's and then we're multiplying this one by I. We're picking this one, dropping the H's, and then getting something like this, another H, and then we're going to continue like inductively getting the I's until we get the I to the end that we want. That's kind of the idea, or why this is a crucial part. And this follows from a very nice application of Feder's criterion. So we have this one because if not, what's going to happen? If this is not contained in here, I can take the column ideal. So one is not going to be here, which means that this column ideal is contained in the maxima. Okay. Take the p to the e powers. Okay. And by the lemma over there, this contains e bracket p to the e to dot I, as long as e is big enough. Claim. This is over because we know once this starts being contained here by Feder's criterion, because the ring is pure, this has an element that is here, but that's not here. That's a contradiction. For this part, we haven't proved the theorem yet. But we're pretty much done because from this observation, I H n minus 1 plus 1. We can just continue. We got this is contained in n I times I H n minus 2. Well, let me just write this as I H n minus 2 plus H plus 1. So this is contained in I H n minus 2 plus 1. And what I was mentioning before, no, we do an inductive problem solution, inductive argument, and this is contained in here. And that's it. So pure rings behave again similar to standard rate rings. Okay. Okay, we have time. Is there any questions so far? Okay. So now I would like to talk about more about the structure of pure rings. And again, a pure split me is the same. So for this, I would like to focus now in that R is local. And this is not problematic because a lot of the properties, like the crucial properties that we're going to get, are localized, no? So we can always reduce to local rings. Okay, so, but we need local because we can define an object. This was introduced, let me just mention, Aberbach and Enescu. So we take a positive number, and then we set, I'm going to write it over here. These ideals, I sub E is equal to all the elements in the ring, such that P R1 over P to the E is inside the maximal ideal for every map that goes from R1 over P to the E to R. Let me mention what these ideals are measuring. What happens if R is outside one of these ideals? Okay. Question? Okay. So if R is outside I sub E, what happens? Then, by definition, there exists a map phi from R1 over P to the E to R, such that P of R1 over P to the E is outside the maximal ideal, no? This is local, so this is, if this is a U must be a unit, no? Then, if I first compose, if I take phi equal to U inverse bar phi, this one, this is also a map that goes from R1 over P to A to R, and this map by construction is equal to U minus 1 phi R1 over P to A, which is U minus 1 times U, which is the identity. So this is telling us all those elements that can go to 1, no? So this is things that split in a way, no? So what we're saying is, you give me a map here, you have here R times R1 over P to A. This is an R submodule. Here I'm looking at the R module generated by this element within 1 over P to the A. Okay. And then I apply this to R, I apply this phi. So this is gonna go here with this inclusion. It goes to it's gonna be an isomorphism, no? That sends this one to 1, no? So this is telling us, because we have, no, we can go back to here, no? Just multiplying by R1 over P to the A, no? So what this diagram is telling us is that R1 over P to the E is isomorphic to R times R1 over P to the E plus something. In the past, we had it with 1. To be a pure, this has to happen for 1, no? So, and we know that happens. 1 is never going to be here because it's a pure. It's pretty much. This has to be a proper identity. No, that's because they are pure. Oh, my God, a pure. Sorry. And then here, let me just a pure here. Just assume. So, I'm sorry. So because if it is a pure, this is a proper identity, and 1 is never here. And here is telling us, okay, we know that 1 splits of R1 over P. But this is telling me that there might be every element that is not here also split off. Making sense? For every element that's not here that you give me, I can build a free direct summand of this model. We good? Okay. So, if you recall la que llamamos lemma, to compute the minimal number of generators of this element, the minimal number of generators is the dimension over k of m R1 over P to the A, no?
Why does that theory imply that it has to be proper?
Because being a pure is equivalent to be a split, no? If a split tells us that this is a map. Let me get the right one. No, yeah. So what does it pure? Is that you have R, you have the inclusion, R1 over P to the A, and then we have and splitting back beta. And this beta composed with identity is equal to, beta composed with inclusion is the identity, no? Evaluate this at 1. So this telling us that beta of 1 is equal to 1. So there is a map from R1 over P to the A to R that sends 1 to 1, which is outside the maximal identity. So, okay, back. Nakayama's lemma tells us that this is equal to the minimal number of generators of R1 over P to the A, no? For every model. Yeah. And you even did, by the way, I'm sorry for the typo, some examples where this is equal to the degree of this extension times the dimension over k of R m bracket P to the A, no? You haven't done this problem? I mean, this is very similar to the problem you did. Okay? So, in a way, the ideal m bracket P to the A is telling us how many generators do we have in this. Okay. Well, now, what I want to know is, I don't want to see the generators. I want to see the generators of a free part. Here is telling me that I can extract a free part with R1 over P to the A, something is not there. Well, maybe I can extract more. What is the idea that's playing the role? Well, M bracket P to the A is telling me how many generators I can get. By construction, this is going to tell me how many free generators I can extract. So, what we're going to have is that the dimension over K of R E, this one, which we know that is, well, it's contained in the maximal ideal. We haven't seen that this is finite. Quick exercise. Well, well, let me finish this and then I do the second one. So this one is going to be, again, 1 over P to the A times K times the free rank free rank of R1 over P today. What I mean by the free rank, so you have a model M, and then you can write it as R to the A in free plus something, and this has no free direct summand. Then A is what is called the free rank. Okay. So this is telling us the maximum free model that we can extract. If we were in a complete local ring or in the graded setting, we know that every model can be written as a direct sum of indecomposable. So you do that, and then you get, oh, how many free do you have? But here, because we're not looking at any indecomposable, we're looking at free models. We don't need this decomposition theorem. It can be done even if the ring is not complete. Okay. So this is the free mass. Yeah. So this is measuring the freeness of this part, no? And remember, freeness is of the model of ring of p roots is in correspondence with the smoothness of the algebra, no? There is a relation there. And we're going to start exploiting this relation, because even if this is not free, it may tell us that if this is not free, it may tell us, sorry, if this is not free, the free rank is telling us how free it is, and then maybe it can tell us how singular it is or how far from irregular it is. And we're going to use this to measure singularities. Okay, so, okay, I need to do several stuff. First, let's see that why this is finite length. So an observation is that M bracket P to the E is always contained in A sub E. Why? Because if you give me any R inside, let's take a generator here, R P to the E, let's take R inside M, so then R P to the E is inside here, no? Bracket P to the E. And this is generated by elements this shape. So it's enough to check that these ones are contained here. Okay, so let phi be any map from R1 over P to the E to R. Any map. So what is R1 P to the E? What P to the E? No, that's how we compute this definition, no? What is this? This is the same as phi of R, no? Because this cancels with this. And then phi is our linear, no? So this is the same as R phi of 1. I don't care what is phi of 1. I know that because R is in M, this has to be contained in M. We're done. Because this one is, we know that this is cofinite with the powers of the maximal ideal. So this has to be finite length, well, finite colength. So this has to be finite colength. So this model over here has finite length. And this makes sense. Is there any questions so far? Okay. Yeah, I'm gonna put a new problem set that has a few exercises to get more familiar with these ideas. Let me give you just one now. This E bracket P is contained in E plus 1. So this is like this format of P family. Yes, P family, P system. Family. Okay. And it depends how far. Well, no, it's probably. No. I was gonna say sorry. It depends how fast we go, or like I don't want to go that fast. No, but if we do have time, we may see how if you're familiar with the Hilbert-Thermal multiplicity, that's just the limit of colline's of the powers of the L modulo, but normalized, no, modulo n to the d with some factor, no, this factor. So you can do collects of this one and then factor over p to the ed, which modulo p to the ed, which is kind of the normalizing factor here. Find either this or this one, and then you get very important invariance in prime characteristic. Not the one given by this is the Hilbert-Kunz multiplicity, which behaves in some sense similar to the Hilbert-Thermal, but it's a bit more subtle. And this is what's called the singularity signature. And we're going to discuss that if we have time, maybe the last day. Okay. If not, at least I'm going to put a worksheet on the Google Drive so you can have fun on the weekend. You need to have even more fun on the weekend. Okay, so an observation. Kunz theorem, the one of the first one that we discussed is this model is free if and only if the ring is singular, no? It's regular. What does it mean this to be free? Well, it means that every minimal set of generator is a basis, no? So, from Kunz theorem, this follows from Kunz, is I sub E is equal to n bracket p to the a. This is a different way to say that the model is free, no? Every minimal generator is part of a basis. This happens if and only if R is regular. So right there, there is some singularities going on. Let me do this proposition definition. The idea, I'm going to note this curly P equal to the intersection of I sub E, I sub E. This is a parameter, and it's called the splitting prime of R. So I saw yesterday a few posters that use rings of differential operators, and next week you have a mini course with Claudio Polini, which is also includes differential operators. So an exercise for next week, if you end up seeing differential operators in prime characteristic, is show that this is the submodel of the ring. So this is stable over every differential operator. Even further, it is the biggest non-trivial, so it's the biggest proper ideal that is stable under the action of the differential operators. So even though we're playing with characteristic P, this has a differential structure.
Still assuming it's pure.
Pardon me? Yeah, pure, yeah. That's a random observation. Yeah. Yes, definitely. Yeah, if not the pure, then these are not going to be proper, and then P is R, and then R is not that.
Please, what is the proposition part of the definition of the prime ideal?
That is a prime ideal. The definition is given with the name. Okay, actually, it's one time excuse to sit a little bit. Okay, so let's prove this. And what is the? Let's prove this. Okay. So we already know that this is an ideal, not because it's intersection of ideals. So let's prove this. So let A and B be elements outside this splitting prime. Okay? Well, this is this either. So then there exists a need such that let's see, there exists a E prime such that A is outside A sub E and B is outside B sub E prime.
E not in P.
Then, okay, so so that means that there exist phi and bar phi maps from 1 over P to the E minus to R, such that so phi from R 1 over P to the E to R, phi R 1 over P to the E prime to R, such that phi of A 1 over P is equal to 1, and phi of B 1 over P to the E prime is equal to 1. Because we know that not being maximal ideal is pretty much equivalent to just have something that sends this to 1, no? Are we good so far? Okay. So, you remember the here is where we can use the magic of our some sort of dynamical system or fractal. Okay. So I have phi that sends what we're gonna build is an element. What we want to build, let me just give you the preview before I do the proof, because this is a little bit more motivated. So we're gonna build an FC that goes from R 1 over P to the E plus E prime to R that sends the product of these two E plus E prime to 1. And for that, we're going to play with these ones. So what we're going to take is, we set phi, so we have phi from R1 over P to the E to R. This is what we have right now, phi, no? So we're going to set phi tilde plus E prime 1 over P E prime. Okay, so we're taking 1 over P to the E roots of that map. And what we're going to do with this, this sends R1 over P to the E plus E prime goes to phi. Phi only we know to do it for this kind of roots with only the E, so we do it R1 over P to the E. But we have to take out the elements here. So this has to be 1 over P to the E prime. This is well defined, and because phi is R linear, this map is going to be R1 over P prime linear. Here we're just using our fractal. We're moving it from the position E to the position E plus E prime. Okay. So what does this map do? Phi tilde of A 1 over P to the E plus E prime. Where it goes? Well, this goes to phi of A 1 over P to the E 1 over P to the E prime, which is equal to 1 over P E prime. Because we're in prime characteristic, one has only, and the ring is secure, one has only one root, no? Which is 1. Okay? So now, we're going to take the map phi recomposed with, bar phi recomposed with phi tilde. It goes from 1 over P to the E plus E prime. This just goes now to R, no? Because we move from P prime from here to here, and then with bar phi from here to R. Making sense? And then if we evaluate this one in B 1 over P to the E prime times A 1 over P to the E plus E prime. Where this goes? Well, this is going to be equal to phi over phi times this of B 1 over P E prime, A 1 over P E plus E prime. This map, the first map, phi tilde, is 1 over P to the E prime linear, no? So this is going to be the same as phi, B 1 over P to the E prime, times phi of A 1 over P to the E plus E prime. But we know that this is 1, so this is the same as phi of B 1 over P to the E prime, which we know is 1. Okay? We're not quite there, but we're close enough. So what we're going to take is a map, or map FC that we want over there.
You need a tilde and a P.
Yeah, yes. That's only one. Are we good? Okay, so map FC is going to be taking phi composed with bar phi composed with phi tilde composed with multiplication by P by B to 1 over P to the E plus E prime. No. Yeah, no, that B to 1 over P to the E minus 1 over P to the E plus E prime. Okay? So what happens now? If I take FC and evaluate this in A to the 1 over A times B 1 over P to the E plus E prime, this is going to be the same as FC of A 1 over P to the E plus E prime, B 1 over P to the E plus E prime, which is equal to phi bar phi tilde of B 1 over P to the E minus prime 1 over P to the E plus E prime times A 1 over P to the E plus E prime times B 1 over P to the E plus E prime. This times this is going to be here A 1 over P to the E plus E prime times B 1 over P to the E prime. This evaluated at phi bar phi tilde, which we already know that is 1. And we will the thing that we wanted. So this is a prime idea. Okay. Let me use this opportunity to define an invariant, even though we're not going to work with it right now, but maybe tomorrow. Definition. The splitting dimension of R is defined by as dim of R is equal to dim of R modulo the splitting prime. Okay. So this is going to be a very special domain or a very special irreducible variety in the spectrum of R. So that its dimension is something that we may or may not prove tomorrow. So I'm gonna tell you to you now. No, sorry. I have this internal conflict sometimes. I'm gonna tell you, but it's gonna be a cooler theorem. So yeah, and no, because I haven't proved it. So, I'm gonna tell you, just not today. Okay? I'm gonna control myself and then go ahead. Okay. Let me give you now. We have 20 minutes. Theorem definition. Suppose. Oh no, what is not that superior? No, set B sub E equal to the maximum T such that M to the T is not contained in M bracket E. If you want to have some fun, no, just this one. So, sorry, probably it was too much coffee. I have to learn how to regulate it. Let me just drink some water. So this number, I claim that is well defined. So I'm saying it's a maximum. So this is, a natural number. It's a maximum. Then we expect this to be bounded, no? So how we see that this is bounded? Well, we know that this contains M bracket P to the E, no? This contains M bracket P to the E. And we know that M to the number of generators, M to the number of generators times P to the E is contained there, no? That's how we show that Frobenius powers is cofinal with the ordinary powers, no? So this number is at most the number of generators times P to the E minus 1, no? So this number is always smaller than mu P to the E. It makes sense to talk about the maximum. Okay? So the pure threshold of R is defined by, we're going to write FPT of R is equal to the limit of BE over P to the E when E goes to infinity. This is the theorem part of the definition. We're going to prove that this limit actually exists. We can see that this is going to be bounded by the number of generators of the maximal layer, or the embedding dimension of the ring. Okay? This number is very important for singularity theory. Something that I can tell you right now is, let me just make up a sales speech before we prove the theorem. We're going to do that. But let me tell you why two things why this is interesting. Theorem 1, this is Takagi-Watanabe. It is that R is regular even only if the FPT of R is equal to its dimension. So this number detects regularity. No? Look what it is. This number is telling us somehow the splitter order, no? It's telling us what's the maximum order that we can have for an element that is an splitting, no? The split of R1 over P to the E, no? Because this is what this thing is measuring, no? This identity. So this is somehow the E splitting order. And then we normalize by the appropriate exponent. So this we can think like a some sort of asymptotic splitting order. And what's telling us is if the splitting order is D, then the ring is regular. In fact, this is going to be the maximum. Something that they prove is that FPT of R is always smaller or equal than the dimension. So if it reaches its maximum, it's going to be regular. No? So the smaller FPT, worse singularity. It's a way that we can think of. And then a theorem that is even work with Stephanie, Grifo, and myself is the FPT. We're going to do a bit more of this. And in the paper it's written a little bit different, but this FPT is smaller or equal than depth of R. So bigger FPT, bigger depth. So it can help us to see whether something is Cauchy-Macaulay or is bigger FPT, the closer to be Cauchy-Macaulay for a ring. Yeah, and this is, yeah. In fact, one can prove also, this is, no, I just did it that way, sorry. Okay? So let's just prove the theorem. Proof of the theorem. Let's see that the limit exists in the next 15 minutes. Okay? So let R inside M to the PE minus B sub E. We can take an element there by construction, by definition of B sub E. Then, by definition, there exists phi from R1 over P to the E to R, such that R1 over P to the E goes to 1. So, now, because this is the ring is a pure, so F split, we also have that there exists a beta from 1 over P to the E to R that sends 1 to 1. Remember, F split was equivalent to do it for P equals 1, for any P positive, any E positive, or for every E. So I'm using the every E part. Okay, so we can do this because F split. And now we're going to use again our fractal structure. We're going to build beta tilde that goes from R 1 over P to the E plus 1 to R 1 over P to the E. So we take P to the E roots to this map, the same way as we did before. F 1 over P to the E plus 1 goes to beta of F 1 over P, and then 1 over P to the E. And this map is going to be R1 over P to the E linear. So let me just write it, which is R1 over P to the E linear. Okay?
For beta, is it just hard to 1 over P?
Oh. Thank you, Jack. Okay, so now we set phi from R1 over P to the E plus 1 to R, which is going to be given by phi is equal to bar, no. Yeah, no. To beta composed with bar phi composed with beta, no? So we go from beta tilde. We go from beta tilde from here to here, and then we do the next step from here to here with phi. Okay. Are we good so far? Okay. Okay, so Let me see my notes. What I'm saying. Okay, yeah. So let's see what this phi evaluated at. I'm gonna do it with this element as R, but this time I'm gonna do P over P to the E plus 1. Okay? So remember, this is just phi of R to the P 1 over P to the E plus 1. No? What I want to see is that R to the P is outside E sub E plus 1. That's kind of what I want to see that this element goes to 1. Okay, so let's do it. So this is the same as bar phi beta tilde of R 1 over P to the E. Beta tilde is R1 over P to the E linear, no? So this is the same as phi of R1 over P to the E beta tilde of 1. But beta tilde of 1 is 1 because that's what beta does. Phi of R1 over P to the E, but phi 1 over P to the E is 1. No? So we have that this element to this root goes to 1. That by definition, this implies that Rp is outside in A to the E plus 1. But by construction, because R is in M to B to the E, then R to the P is inside M P times B to the E. So we found an element, using an element in M B to E, we got an element in MP times B sub E. So this is telling us that B sub E plus 1 has to be bigger or equal than P B sub E, no? Because B sub E plus 1 is the order of the biggest element that splits off, no? So we have something that splits off here, but it may be something bigger, no? We could probably get something bigger. So what this is telling us, then, if we look at the sequence, let's just divide here by P to the E plus 1. This divided by P to the E plus 1, we get P to the E, no? So the sequence, B sub E over P to the E, is non-decreasing and bounded. Therefore, it converges. Let's do some examples before we go for the coffee break. So one example, FPT of a power series ring, or for that matter, for every regular ring, we know from that theorem that this is equal to the dimension, no? That's not so interesting. FPT of, let's take a power series ring and take the equation for an ideal generated for monomials. Since this has been a theme. Okay. So this is equal to the number of variables that do not appear in any minimal generator of I, monomial minimal generator. In a minimal monomial generator. Another way to see it is, if we call this, let me call it A, that means that this ring K of X over I can be written as K on some variables, Y over an ideal J, and this J, every minimal generator has at least one of the variables, and this can be here. And then this number of variables is exactly A. And then we finished today. Well, I'm going to give you some exercises about computation, so I don't want to do it. No, like yesterday I did only one example of a pure ring, but then you saw a lot in the problem set. So expect some examples today. Okay. So an open question is a PT of R a rational number. This is known for several cases. There's a bunch of literature. So I want to say names because I'm going to forget one case and one name. But there is a bunch of examples. But to the best of my knowledge, it's still open in general. Yeah. Okay. So that's it for today. Thank you.